Welcome to G Fun Facts Online. Today we are diving deep into a subject that sits at the intersection of existential dread and cutting-edge physics. We are talking about planetary defense, not the science fiction version with oil drillers and dramatic goodbyes, but the real, hard science that is currently being developed to stop the sky from falling. Specifically, we are looking at a major breakthrough published in late 2024 by physicists at Sandia National Laboratories that fundamentally changes how we might save the world from an asteroid impact. It turns out, the solution isn't about brute force destruction. It is about a concept called the nuclear nudge. For decades, the idea of an asteroid impact has been the ultimate cosmic nightmare. We are talking about a mountain-sized rock hurtling through the void, destined to cross paths with Earth. In Hollywood, the solution is always to blow it up. You send a team to drill a hole, drop a nuke inside, and detonate. But in the quiet, sterile halls of real-world science, that is actually the last thing you want to do. If you blow up an asteroid, you turn a single cannonball into a shotgun blast of radioactive buckshot, all of which is still heading toward Earth. You do not want disruption. You want deflection. You want to shove the rock, not shatter it. Before we get into the new technology, we have to understand the enemy and our previous attempts to fight it. Near-Earth objects, or NEOs, range from pebbles that burn up as shooting stars to behemoths capable of ending civilizations. Until very recently, humanity had one primary defense strategy called the kinetic impactor. The concept is incredibly simple. You slam a spacecraft into the asteroid at high speed to transfer momentum, slightly altering its orbit. We actually proved this works. On September 26, 2022, NASA conducted the DART mission, or Double Asteroid Redirection Test. They crashed a spacecraft, roughly the size of a vending machine, into a moonlit asteroid called Dimorphos. It was a massive success, shortening Dimorphos' orbit around its parent body by 32 minutes. However, while DART was a victory, it also highlighted the terrifying limitations of kinetic impactors. First, there is a mass limit. DART worked on a moonlet, only 160 meters wide. But if we are facing a city killer, an asteroid that is 4 kilometers wide, a single spacecraft is like a mosquito hitting a semi-truck. You would need thousands of darts, or a spacecraft so massive, it would be impossible to launch. Second, kinetic deflection requires years, or even decades, of lead time. The change in velocity is so small that it needs a very long time to compound into a safe miss distance. And finally, we often don't know what an asteroid is made of. If it is a rubble pile, which is just a loose collection of rocks held together by weak gravity, a kinetic impactor might just get absorbed like a bullet into a sandbag, failing to push it at all. We needed a weapon with significantly higher energy density. We needed something that could deliver a massive shove in a fraction of a second. This brings us to the breakthrough at Sandia National Laboratories. The team there, led by Nathan Moore, decided to look at our most destructive weapon, the nuclear bomb, and repurpose it as a shield. But the mechanism is not what you think. They validated a strategy called a standoff detonation. In this scenario, a nuclear device is detonated a few kilometers away from the asteroid's surface, not inside it. When a nuclear explosion happens in space, roughly 70 to 80% of its energy is released as high-intensity X-rays. These X-rays travel at the speed of light and slam into the side of the asteroid facing the blast. This is where the physics gets incredible. The outer layer of the asteroid's rock, only a few microns to millimeters deep, is instantly heated to tens of thousands of degrees. It does not just melt, it sublimates. This means it turns directly from solid rock into expanding gas and plasma. This rapidly expanding gas explodes outward into space. Now we have to remember Newton's third law. For every action, there is an equal and opposite reaction. The force of this gas shooting away from the asteroid acts like a rocket engine, imparting a massive thrust into the asteroid, pushing it in the opposite direction. Effectively, the X-rays turn the asteroid's own surface into a rocket engine for a split second. This theory has existed for a while, but proving it was a massive challenge. You cannot simply launch a nuclear weapon into space to test a hypothesis. The 1967 Outer Space Treaty bans the placement and testing of nuclear weapons in orbit, so Moore and his team had to get creative. They realized they did not need the actual nuke. They just needed the X-rays. To do this, they utilized the Z-machine at Sandia National Laboratories in Albuquerque, New Mexico. The Z-machine is the most powerful pulsed power generator on Earth. It is a technological titan capable of discharging electrical currents unmatched by any lightning bolt. The machine works by storing huge amounts of electricity in banks of capacitors. In a microsecond, it releases this energy into a target area the size of a spool of thread. This creates a magnetic field so intense it crushes argon gas atoms together, creating a superheated plasma that emits a burst of X-rays powerful enough to simulate a nuclear detonation. But there was still one more problem to solve, and that was gravity. In space, an asteroid floats freely. In the lab, if you hang a target up, it is pulled down by Earth's gravity. If you hold it with clamps, the clamps absorb the shock. If you hang it by a string, the string interferes with the data. Moore's team devised a brilliant solution they dubbed X-ray scissors. They suspended a mock asteroid, which was a 12-millimeter grain of silica or quartz, using a foil filament 8 times thinner than a human hair. When the Z-machine fired, the initial burst of radiation instantly vaporized the foil, effectively cutting the target loose. For a few millionths of a second, the target was in true freefall, floating as if it were in deep space. In that exact window, the main X-ray pulse hit the target. The results were staggering. The X-ray pulse hit the silica target, vaporizing its surface just as predicted. The resulting plume of gas accelerated that tiny rock to 69.5 meters per second. That is over 150 miles per hour, achieved in a fraction of a second. Moore explained that it was exactly like a rocket engine. The synthetic asteroids were not smashed, they were shoved. This experiment proved that the momentum transfer was not just a theoretical equation, it was a measurable, scalable, physical reality. The most important part of this study is what the data tells us when we scale it up. The scaling laws derived from the Z-machine data suggest that this method could deflect an asteroid up to 4 kilometers, or 2.5 miles wide. To put that in perspective, the asteroid that wiped out the dinosaurs was about 10 kilometers wide. The standard catastrophic movie scenario usually involves a rock that is 1 to 2 kilometers wide. A 4-kilometer asteroid is an extinction-level event for human civilization. The study indicates that a nuclear standoff burst could impart enough velocity change to push such a monster off an Earth-intersecting trajectory. This provides a critical advantage regarding time. If we discover an asteroid is going to hit Earth in 6 months, a kinetic impactor like DART is useless. It simply cannot deliver enough energy to change the path in time. A nuclear device, however, packs millions of times more energy per kilogram of payload. Moore's research suggests that even with short warning times, the sheer force of X-ray ablation could provide the desperate, high-energy shove needed to clear the Earth. This method also addresses the issue of asteroid composition. As we mentioned, some asteroids like Bennu are rubble piles. Critics previously worried that a nuke would simply scatter a rubble pile. However, the Sandia experiment shows that because the X-rays only interact with the surface, the top few millimeters, the shockwave does not necessarily have to travel through the whole body to move it. The rocket effect pushes against the surface, and gravity drags the rest of the rubble pile along with it. The team plans to test more complex makeups in the future, including iron-nickel composites and porous rocks, to simulate the wide variety of asteroid compositions found in our solar system. Of course, while the science is sound, the implementation is politically explosive. Article 4 of the Outer Space Treaty explicitly forbids placing objects carrying nuclear weapons in orbit. There is a potential loophole, as the treaty bans stationing weapons, and it is legally ambiguous whether launching a weapon from Earth to intercept an asteroid constitutes stationing. However, international trust is a major hurdle. If the US or China announces it is launching a massive nuclear warhead into space to stop an asteroid, other nations might fear it is a disguised attack. For the nuclear nudge to be a viable strategy, the world needs a new legal framework and rapid response protocols verified by international bodies. Currently, NASA has a Planetary Defense Coordination Office, which would likely serve as the command center, along with partners like the European Space Agency. The new Sandia findings likely push the nuclear option from a theoretical last resort to a primary strategy for large objects or late detected threats. Looking forward, the success of the Z-machine experiments marks the beginning of a new era. Nathan Moore's goal is to create a library of deflection. He envisions a database where, if an asteroid is spotted, we can look up its composition, size, and porosity. The library will then tell us exactly what yield of warhead is needed, what standoff distance is optimal, and where to detonate to maximize the deflection. The future of Earth's defense will likely be a layered system. Layer 1 involves early warning via space telescopes, like the upcoming NEO-Surveyor spotting threats decades out. Layer 2 uses kinetic impactors for smaller rocks with long lead times, as they are cleaner and politically safer. And Layer 3 is the nuclear nudge, reserved for the city killers and planet killers, or any rock detected with less than 5 years to impact. For nearly 80 years, nuclear technology has been the specter of humanity's self-destruction. It is poetic irony that the same physics used to build the ultimate weapon may be the only thing capable of ensuring our survival against the universe's most ancient violence. The dinosaurs did not have a space program. They did not have the Z-machine. We do. And because of the work of scientists like Nathan Moore, when the next great rock comes for us, we will not just watch the sky fall. We will push it back. That concludes our deep dive into the nuclear nudge. Thank you for listening to G Fun Facts Online.